Greetings. In this video, we'll talk about the calculation of an area bounded by, in this case, the x-axis. So we're considering some function. Of course, we're taking a definite integral to get the area, because this function, this particular one that we're going to use in this case, is f of x, and the f of x will be sine x. So as we use this one, how it will look on the graph is something like this. And let's take into account the interval 0 to 2 pi. Right, this is the y-axis, this is the f of x, and this is along x. This is the x-axis. If we're taking 0 to 2 pi on sine x is here. So here's the end of the interval we're taking into account. Here it was 0, so here's the beginning. And when we're talking about area bounded by an axis, is basically all the areas where the curve goes further away than being at the axis. So whenever the curve is away from the axis, the area between it and the axis will be taken into account. So it's both this and this part. These two parts, taking the usual integral, if I did integral from 0 to 2 pi of the function which we see it's sine x, if I do it the usual way, definite integral classic way, well, that will do its job, but it won't be the area bounded by the x-axis. It will simply be the accumulation in respect to the x-axis of f of x here, but what is below the x-axis will get subtracted the same way like what is above creates the positive value. That means if we had some value on this part, if this volume above x was some value, then this remaining part, pi, here is pi on x, pi to 2 pi will then be the negative, because actually here is the same volume like it was here, the same area. So pi to 2 pi will subtract it. Anything that's below the x-axis again subtracts away from the value of the definite integrals result. Therefore, what we want to do really is, when we're talking about area bounded by the x-axis, we're talking about all the areas they are strictly between the curve and the x-axis, regardless of whether if they are below or above. In the terms of usual integration, we can basically say that what we are actually integrating is the absolute value of the function. So I put the absolute value sign around the function that's integrated. Well, that's not gonna be taken care of automatically. So what we are doing here is we disregard the fact that by default the definite integration would subtract what's below the x-axis. So this area would get subtracted from what this created. We want both of these areas to be taken into account. Strictly just say how much area there is generated between the curve and the x-axis from 0 to 2 pi, regardless whether if it's below or above. Both is counted and neither has a subtractive effect. So yes, what I did is basically I did an absolute value which does not affect 0 to pi, but the parts that were below will get switched above. So this would be the absolute value version of it. I just show it here. So the parts that were below will suddenly be above. This is the absolute value version that arises. So what we are doing here is, just like absolute value usually, when something is already positive, it does not affect it. Something is negative, it switches it to positive. So if I'm trying to get the area bounded by the x-axis from 0 to 2 pi, what I do is I can break out the integral like it's usually done. We just take the interval of the definite integral considered and break it out into parts that make sense, and we have to take into account the entire interval eventually. So in this particular case, I'm going to break it out 0 to 2 pi and then pi to 2 pi. So 0 to pi and pi to 2 pi. Because 0 to pi, I don't have to put the absolute value. So 0 to pi, I'll do sine x simply. Sine x dx. Like this. And to that I add pi to 2 pi of again sine x, but this time I have to put it in the absolute value. So to calculate the area bounded is to take any intervals where the function is below the x-axis and put those intervals into absolute value. So now we can finally finish this. There's more ways to consider how to now continue, but let's just follow the path and see where it leads. So 0 to pi sine x dx, first of all get the antiderivative, that's cosine x, and normally evaluate it. This part we said nothing's gonna change because it's above x anyway. And then the second part, because it's in absolute value, and we know it's in absolute value because the value would be exactly -1 times different than what we want. It would be just switch to negative. We will actually multiply it back to positive by -1 and add integral of sine x without the absolute sign, integrate it from pi to 2 pi. Of course, I could also realize that this part is the same area like the 0 to pi and just multiply that part twice, which would be done in more complex examples, of course, but here let's just do it the slower way, and let's just say, okay, so this part pi to 2 pi is negative, so we're gonna make it back positive by -1, and then I'm gonna integrate what I wanted to integrate, which is minus cosine x is the antiderivative of sine x, and evaluate at 2 pi and pi. So the only thing we had to do is multiply by -1 to make sure that the negative part was gonna become positive. So let's finally evaluate this. What this will basically give is minus cosine of pi should be 1 minus cosine, we subtract it, minus cosine of 0 will be 1 also, so it's 1 plus 1, and then add to it -1 times minus cosine will be just plus cosine of 2 pi should be 1, and minus cosine of pi should be also 1, so the result should be 4. So that's the result. It can be verified using some digital software, of course, but this is the way to approach it. What we had to do when calculating the area bounded by the x-axis was to switch the intervals on which the function f of x was negative into its absolute value.